Okay, thanks. So I'm going to talk about incentivizing exploration, which is a common model. I'll describe to you what that means, a common model in the CS literature. And I'm going to focus on solving it in a case with behavioral agents and imposing that we use what we're going to call unbiased histories as signals for these behavioral agents. And this is joint work with Zhiming Mao, who actually is now at Facebook, Alex Lifkins, and Stephen Wu. So in this incentivized exploration literature, we have a sequence of agents who are coming one by one to a system and choosing an action that has some unknown payoff. So they're going to get a stochastic reward from some unknown distribution. And these decisions of the agents are going to be coordinated by a principle. This could be like a recommendation system, for example, that is trying to suggest to the agents what actions they might take and thereby what rewards they might get. Applications, so we saw this a bit in Nicole's talk yesterday, might be things like you're trying to choose a restaurant in a new city, so tourists come one by one. They go to Yelp, they see what the recommendations are on Yelp, and then they pick a restaurant and they get some payoff based on the quality of the restaurant, which is something stochastic. And so then Yelp would be the coordinating principle trying to help the agents find the best restaurants in aggregate over the population. You could have other applications as well. You might be buying products and each product has some quality and you're trying to be Amazon or something like that and trying to help the agents find the product of high quality. You could be choosing medical treatments and here each medical treatment might have a different health outcome. But importantly, in this literature and in the case I'm studying today, the payoff of a particular choice is going to be a common value object. So everybody has the same value for, or that gets the same stochastic reward for the action, for a fixed action. And so this is related, of course, to the multi-armed bandit literature. This is basically the multi-armed bandit problem if we don't have agents muddying up the waters. So what are the multi-armed bandit problem? We have, I'm going to be focusing on a case of two arms throughout this talk. And so there's going to be the red triangle arm and the blue diamond arm. And the multi-armed bandit algorithm is going to sequentially pull one of these two arms and receive a stochastic reward. I'm going to be focusing on a case in which the reward is either 1 or 0. And the important statistic then is the probability with which a particular arm returns a reward of 1. And so each arm is parameterized by a coin, which has some unknown bias. And the algorithm is going to pick an arm. And when it picks an arm, what happens is that coin of that unknown bias gets flipped, and the algorithm observes the reward of the coin. So the algorithm will just observe 1 if the coin flip came up heads and 0 if it's tails, but it doesn't know the bias with which the coin was flipped. And so this is the multi-armed bandit problem. The algorithm gets to decide how to pull these arms in order to try and maximize the reward that it receives over some fixed time horizon. In the incentivized exploration problem, we have a centralized planner. And what the centralized planner would like to do is to always pull the arm with the highest mean reward. That would maximize the expected reward over time. So it would like to tell every agent that comes into the system, if it knew the best product or the best arm, the best option, it would tell every agent to pull that arm every time. And what we're going to do in a bandit algorithm, so if we didn't have incentives to worry about, we don't know which arm has the highest mean reward. So we're going to try and pull a sequence of arms that's going to maximize what we call regret. So I think the one thing that you could try to optimize here that people study is the expected reward in a Bayesian setting. But another thing, which is what I'm going to focus on and which we focus on in the computer science case, is algorithms that maximize regret. Regret is going to be defined as the optimal reward of the algorithm, the optimal reward, which is the highest mean reward times the time horizon, minus the reward that the algorithm receives. So we're trying to minimize this difference, okay? And one thing to note about this problem is that for either of these objectives, because you don't know the mean rewards of the arms, any bandit algorithm that's going to be doing well is going to have to do both exploration and exploitation. So it's going to have to explore a bunch to figure out which arms are the better arms. And then it's going to have to leave itself enough time to exploit a bunch in order to pull that arm with the best reward so that it doesn't lose too much compared to opt. Okay, so now how do we deal with the incentives? Well, the arms are going to be pulled in our setting by agents based on signals that they receive from the principal. And so what people have done is they say, okay, let's have the principal commit to a BIC signaling scheme. So these agents are going to be maximizing their, each agent that comes in wants to exploit for him or herself, right? So they want to pull the arm that maximizes their personal reward. And the agent is going to signal to them which arm that is the principal would like the agent to pull. And if that scheme, so notice that there's an information asymmetry here, because the principal knows the outcomes of all of the past arm pulls, but the agent comes into the system and doesn't have that information. And so the principal can leverage this information asymmetry to induce the agent to pull whichever arm the principal wants under some conditions on the signaling scheme. So there's some incentive constraints. The principal is going to commit to a signaling scheme that's going to cause the agents to want to follow the recommendation of the principal. And yeah?
You guys see here as what?
So there's, it stands for Bayesian incentive compatibility, and the agent that's coming into the system has some information, some prior over the mean rewards, and knows this signaling scheme, so it knows the mapping from whatever the principal knows to the action. And it has to be that when I do my update on my prior and the output of the signaling scheme, given what I know about this mapping, that my best action is to follow the recommendation. And so, then if that's the case, then the agent's going to pull the recommended arm. So the principal can pick any signaling scheme that induces this kind of behavior. And the objective is to pick one that's going to minimize the regret. Yes?
The agent only knows the number and the signal?
The agent knows their number and the signal they receive, yes. And whatever prior they have over the mean rewards of the arms. And so the question is how the principal can induce exploration for the agents, yes?
I'm just confused. Why are you not calling it persuasion?
It's kind of like a dynamic version of the Bayesian persuasion game, for those of you that know what that is.
So I remember a recent, maybe not that recent anymore, Monty Perry and Elon Kramer, they worked on something similar.
Yeah, there's, I'll list related work there. So I think you're referring to this paper. So, people have been looking at this problem, asking how we can induce agents to explore. And the top two papers here, the Kremer, Mansour, Perry, and Mansour, Slifkin, Serganis, are going to induce explorations by recommending that agents explore with some small probability. And then if, you don't know if you're the agent that I'm recommending that you should explore. Maybe I was actually telling you to exploit. You don't know which coin flip you got. So that's going to induce you to follow the recommendation. And the Fraser, Kempick, Kleinberg paper is going to instead pay agents to explore. And then they get this very nice characterization of the trade-off between explore, exploit based on how much we have to pay agents to explore. Yes?
So initially you have the BIC guarantee is over the initial priors, but then over time do the agents update their priors based on what they observe from their own choice?
They have no they don't come again. They come once. They're tourists in a city. And the nice thing about this setup is that the BIC schemes are going to match the optimal learning algorithm results. So basically the incentives don't hurt us at all in terms of the objective we have in mind. So we can get the optimal regret even with the centralized principles, centralized coordinated principles. Okay, so this is sort of the background. This is what the literature has been doing. That's sort of the classic papers in this area. And here's the motivation that they have in most of the introductions is the idea that there's some website like Yelp, and Yelp has this problem that it doesn't know the quality of the restaurants. It wants to give all of the users the best experience possible. It wants them to go to the best restaurants possible, but it doesn't know which ones are the best. And so it is going to make recommendations. And so here I was visiting Stanford, staying at the Sheridan, which is like kind of right here. And I wanted to go out for Chinese food, and so I searched for Chinese on Yelp, and it gave me this result. And so what you can see is that it gives me, first of all, it doesn't just tell me where to go, as in the setup that we've described so far. It instead gives me a list of options. You might think that, and it doesn't, tell me, it doesn't just give me this list with no explanation. It tells me something about each restaurant, like the rating that it's seen so far, the average rating it's seen so far, and how many reviews it has. And so this is the list I got, and the thing is, you might think that this list is sorted such that Yelp wanted me to go to Taste up there, but looking at this, I see that Garden Fresh has many more reviews and a higher rating, so maybe I prefer to go to Garden Fresh. And so I go there, ignoring, in the sense, the recommendation of the principal, which is to go to Taste. And so I want to think about the disparities between the standard incentivized exploration model that I described and this app that we all use frequently. One thing is, when I was reasoning about where to go, did I think about a prior and do some updating and about the signaling scheme of Yelp and everything? I just kind of looked. I was like, oh, it has more ratings. It has a higher higher average rating, and decided to go there. So one question is, do agents really perform full Bayesian updating? Or is there something behavioral going on about the agents? And how does that impact what the principal can achieve if they aren't fully Bayesian updaters? Another is this classic literature is using sort of a revelation principle style thing to say, oh, I can just tell you where to go and you're going to be incentivized to follow that and it's all fine and dandy. But is it feasible in the context of these applications to just tell somebody where to go? In particular, if we had an app that just said, oh, you want Chinese food, go there, with no explanation, I think we wouldn't really trust it. So they need to have supporting evidence for the recommendations they're making to us. And there's a bunch of other sort of disparities between the classic model and the reality that I'm not going to focus on, but I think are very interesting. We saw one yesterday, which is that restaurants can come and go over time. And so maybe the qualities even drift over time. And so we need to manage that. There's also the idea that consumer search is costly. And so I can do some investigation to figure out, I can go read all the reviews to figure out to get a more refined signal on the quality of the restaurant, but that takes time and that's costly. agents could come in, so somebody mentioned this, Vasilis, I think, like agents could interact with the system repeatedly. That'll break a lot of these models. And then another thing that I've looked at a bit is that we have this common value assumption. But what if agents are inherently heterogeneous in their preferences? Maybe the diversity alone induces enough exploration that we can even just get rid of the coordinating principle if agents are diverse but not too diverse, you know, like maybe Azarach likes Persian food better, and so, but there is an overall best restaurant. So I'll go explore the Chinese food, she'll go explore the Persian food, we'll share information, and we'll find the best restaurant that way. So these are all like other directions that you see in the literature that I think are also very interesting. But today I want to kind of address the top two disparities here, the rationality assumption and the space of signaling schemes that we permit. So we're going to look at a model in which the signals are subhistories. So the principal is required to report the experiences of some subset of agents and not just a recommendation. The agents themselves are going to be frequentists. So instead of doing a Bayesian update, the agents are going to estimate the quality of a restaurant using the empirical average of the outcomes that they've seen in these subhistories. And in under these restrictions and behavioral assumptions, we're going to see that there's a simple scheme that gets you sublinear regret. And then we will refine this scheme to get a multi-layered scheme that has near optimal regret, so it matches the optimal regret bounds. And there's, I think, maybe three main ideas in the proofs that can kind of be like the most salient of which is that there's this idea that we want to group agents into focus groups, which are going to then explore different options because of the stochasticity of the setting. And from that, we can then learn about each of these different options. So let me get into the result a little bit more deeply. So I will first define the setting. I'm going to focus, as I said, on a setting with two arms. And the arms are going to have a mean reward mu a. I'm going to assume that it's, well, really bounded away from 0, but you can think about it as being in the interval 1/3, 2/3. And the reward is going to be 1 with probability mu sub a for arm A, and 0 otherwise. And I'll label the arms such that arm 1 is the better arm. Okay, so mu1 is larger than mu2. The agents, there's going to be some time horizon capital T, and agents are going to be labeled by the time at which they arrive to the system. So we have a sequence of agents, A1, A2, up to A capital T. When the agent arrives, they're given a signal, which is going to be one of these histories of what's happened in the past. You might get different histories if you arrive at different time steps, but you know that up front. And when you get your signal, you're going to choose some arm, and then you're going to receive a reward based on the mean reward of that arm.
So is the signal the perfect history?
No, I am going to have signals are going to be a subset of history. So there's a subset of time steps that I'm going to choose ex ante upfront. And I'll discuss that on a future slide. But there's going to be a subset of time steps, and you are going to see the arm that was pulled and the reward of that arm for every time step in that subset. And that's what you use to choose your, to optimize your action. And this can differ for agents that arrive at different time steps. Yes?
Are those the subsets randomized, or is it deterministic? Or?
Our construction will choose these subsets deterministically. I'm happy to let it be randomized, but I want, I'm jumping ahead a little bit, but I want the choice of which history you see at a particular time step to be chosen ex ante. So I don't want you to let the principal use the history, use the realizations to choose what history to give you. So if it's randomized, flip all the coins in the beginning.
the average of the rewards?
Are what?
Could you have the average of the...
Yeah, so this is going to depend on the behavioral model of the agents. I'm going to, you can list all of them, but because of how I'm assuming agents behave, the average is going to be a sufficient statistic, and I'll discuss that in a moment. Was there another question over here? Yeah?
So that last bullet about, I think, the signals, is that the problem definition or is that the policy's choice?
I am restricting myself to consider policies in this class.
So the class I'm not very clear on, in the sense, what are the constraints on these subsets and so on?
Could be anything. Like any policy which upfront decides at Monday, any agent that comes on Monday is going to see the history of agents that came over the weekend.
So for example, they may see no history.
Yeah.
But they cannot be given a recommendation.
Right. Yeah?
For the frequentist agents, there's no structure on the history, some sort of like nested structure on the history they see in the previous ones.
There will be a structure on the history that's chosen by the policy, and the frequentist agents are going to simply follow this behavioral prescription, which the reason that I'm so insistent on fixing the histories ex ante is to make this seem like a reasonable behavior to follow. So because I'm fixing the histories ex ante, I'm not trying to trick you into only seeing histories where this outcome was good. So the frequentist...
Depends on the time step, right?
Yes.
It does.
Yes, the history does. So the frequentist agents are going to look at a subhistory. They're going to count the number of pulls of a particular arm in that subhistory. So that's on Yelp, like the number of reviews that Yelp has received for that restaurant. They're going to calculate the empirical mean rewards. And so to Gabriel's question, this is why it's sufficient to just report the average. And then they're going to pick an estimate of the reward of that arm, which I'm gonna call empirical mean rewards mu bar A. The actual mean reward is mu A, and the estimates that the agents form, and this is their behavioral choice, is mu hat A. And I'm going to require that mu hat A gets closer to mu bar A as the number of samples grows. So if you don't have very many samples of the arm, I'm letting you do whatever you want. But as you get more and more samples of the arm, you have to get closer and closer to the empirical mean reward. And then the behavior that they follow is they look at all their estimates and they pick the arm with the highest estimate, and let's say that they break ties randomly. So notice that this allows a whole class of behaviors. Like, I'm not saying how they pick their mu hat so long as it's within this distance of the empirical estimates. They could even have, biases. Somebody might prefer Chinese and somebody might prefer Persian food, so long as it's, once they get enough signals on the other restaurant that they don't prefer that, then they might go there, right? So long as they're close to the empirical means. At this point, somebody might ask, what about Bayesian rational agents? Does this behavior capture Bayesian rational agents? That's going to depend, I think, on the priors that they have over the arms. But I prefer to think of these as behavioral agents. Okay, so now let's think about the signals that we can use. So I'm going to require, first of all, the subhistories to be transitive. And so all future diagrams will assume this. But let's suppose, why do I care about transitivity? So what do I mean by transitivity? I mean that if I see what Vasilis sees, and Vasilis sees, what Azarach sees, then I also see what Azarach sees. If it weren't transitive, then I might worry that my behavioral agents are this guy, if this is not transitive, is maybe only seeing these two things, and doesn't know that this guy picked this blue diamond option because he had a lot of information about it. And so I don't, like, then the behavioral assumption starts to get a little sketchy. Like, I want to make sure that everybody's working off of the same set of information in the same path. Yes?
I was a little confused by something you said, that this is consistent with Bayesian agents. Is the reward estimate a strategic choice of the agent, or is it a deterministic function of the history that they see?
They get to pick anything. This can, you know, they have some function that maps the history they see to an estimate mu hat, as does a Bayesian agent, right?
I see, but they're not picking that in a strategic way based on some payoff function. It's just a given.
They are, I mean, if they're fully Bayesian, they're going to find some estimate of the mean reward, and they're going to pick the thing with the highest mean reward.
In that case, it would then depend on the policy of the principal.
Yes, yes, and that's why I said that, like, for some priors and maybe some policies, this might capture the Bayesian. But like, what you have to check is that does the Bayesian agents, the posterior's mean reward actually fall in this interval of the empirical mean reward? If it does, then fine, Bayesian agents are fine.
Does the principal have access to how they form that reward estimate, or all they know is that it's asymptotically close?
This is all they need to know. Okay, so I also, as we've been discussing, want to make sure that we're choosing the subhistory that the agent sees ex ante, because otherwise the principal can basically only show you reviews where this restaurant was highly rated. And then you have to start reasoning about why is the principal, you know, why does this restaurant look so good? Maybe it's because the principal's policy was to only show me reviews where that restaurant was highly rated. But if you choose the signaling scheme, if you choose the subhistory ex ante, the principal can't fool you in this way. They're committing up front before they see the outcomes of the agents that came on those particular days. Okay, so this is the restriction I'm going to impose on the signaling space. And so now the principal is supposed to choose signaling schemes that are going to minimize regret, given the behavioral model of agents. So again, the regret is what the opt receives by pulling the better arm every day, the best arm every day, minus what the principal receives. So in time horizon t, the optimal algorithm is going to get an expected reward of t mu1, because mu1, recall, is the better arm. And the agent is going to get, I mean, the principal is going to get the expectation of the sum over all the agents of the mean reward of the arm that agent pulled. And so that's the optimal utility, and this is the utility that the population enjoys when following, you know, under the existence of this principle. And I want this to be minimized in worst case over the realization of the mean rewards. So over a worst case choice for the mean rewards of the arms.
Can you explain this criteria? Because in some sense, for people, what can understand if there are risk averse, but for the principle, it's not clear that the worst case is, makes sense.
So like, I just want to think about somebody is picking these, like an adversary is picking these mean rewards. And then the principal is trying to minimize this in the worst case over what the, you know, adversary is doing. And like, you know, you're probably preferring to come from some economics approach where you have some distribution over mean rewards, and like you're trying to optimize the expected utility of the agents in a Bayesian sense. So that's not what we're doing. We're trying to do a worst case thing and minimize this difference. We can talk more about the choice of these two objectives offline, but this is the standard one that we use in computer science, I think. It's been inherited from that literature. Okay, so a first attempt would be to let everybody see everything. That seems natural. What's going to happen if I let everybody see everything? So we might have two arms, one which is a bit better than the other, but the better arm is going to get a bunch of bad outcomes in the full history. It's just by chance, the first few times somebody went to that restaurant, they hated it. And so as a result, the empirical mean is going to drop of the better restaurant, and the other restaurant is going to have a high empirical mean. Now, as soon as these empirical means separate by enough, you're going to get the error bars that I'm allowing based on the number of times the arm has been pulled are going to suddenly separate. And now, even if agents' behavioral choices are super optimistic about the red triangle and pessimistic about the diamond, they nonetheless are going to assume that the diamond is better than the triangle. And thereafter, everybody's going to go to the diamond. We're never going to update about the triangle. And essentially, we've herded. This is slightly different from the herding literature in economics, but it's kind of like we've herded on this suboptimal option. And so that doesn't work. There's these. You just get. You can show that you just need a constant number of bad draws to have this separation occur. And so we get a constant probability that we end up all pulling the suboptimal arm, and then we're going to have linear regret. So the other thing that's pretty natural is to have no history at first. And so for this setting, let's suppose that we know the gap. Let's first imagine that we know the gap between the reward of the best arm and the second best arm. And in that case, and let's say that with no information, agents are going to choose an arm at random. This is just kind of for convenience. We'll see that we don't actually need that in the policy we really design. But now let's imagine no history at first. This is a policy which is going to have some number of k agents appear in the system. And then thereafter, and with no history at all. So these guys don't get any history. And then thereafter, everybody sees the outcomes of those k agents only. What's that going to do? There's this theorem in statistics. This is, I have two biased coins. Can I distinguish which one's the better coin? And so it's not hard to calculate that you can distinguish biased coins with high probability using a low number of samples, which scales like 1 over delta squared when the gap between the bias of the coins is delta. And so using that theorem, we can calculate the regret that you would get from this example. And this is all sort of very standard stuff in computer science. I just want to do it so you see what the proof looks like. So you set, you notice that the optimal plan is going to get, as we've said, t times mu1, the mean reward of the better arm. The plan with no history is going to get k mu2. That's these first k agents are getting at least the reward of the worse arm, which is mu2. And the remaining t minus k agents, well, if this event happened, that the coins were distinguished, then they're going to pull the better one because the gap is large enough and they've seen enough samples that even their estimates are going to cause them to pull the better one. And in the event that the coins weren't distinguished, we can't say anything, so let's say they get mu2. Now you take the difference of these two things, and you get something that's, if you set k appropriately, is like log t over delta. So this is the regret of no history. But notice that it required us to know delta, the gaps in the arms, in order to decide how many agents to give no history to. And so we can improve, we can avoid needing to know this with simple algorithms. And this is, following what you would expect if you know the multi-arm bandit literature. We can get a regret of t to the 2/3. And I'm hiding this tilde here, means I'm hiding log factors in what I'm going to call a 2-level policy. I can get improved regret if I add one extra layer to my policy. And then with another trick, I can get a multi-layer policy that gets near optimal regret. So as k grows, this approaches 1/2. And notice that with non-adaptive policies and multi-arm bandits, the optimal regret is t to the 2/3, which is what I'm getting with my 2-level policy. And in adaptive policies and multi-arm bandits get regret like t to the 1/2, which is what I'm getting basically with my multi-layer policy. Yes?
I'm a bit confused. Maybe you said like statistically you can distinguish the arms, but you're taking the worst case over the draws, and I'm not really sure how to fit those two things together.
She's not taking the worst case over the draws, but rather over the means.
Oh, you still like the adversary is just setting distributions.
Yeah, yeah.
So, in the initial phase when you don't show any history, the agents are just picking something at random.
That's what I'm assuming for that analysis. But
why isn't it just like the non-adaptive?
it is basically. To get rid of, so in my 2 levels, I'm going to basically just blow up those guys that are picking something at random large enough that even if they're picking something deterministically, like if they always favor arm 2, then there's enough samples of arm 2 that it drops below arm 1, and then they, if you're happy for them to pick something random, then that is the 2-level policy. If you're not, then you can do this thing where they're going to eventually figure out that the other arm, like they're gonna, each arm is going to get unlucky and get enough bad draws that they're going to be induced to pull the other arm no matter how they're picking their estimates. Okay, so that's how we get to level 2. We create a level 1 where we have a bunch of different groups, and in each group we have this full history policy that we saw earlier, which might, with constant probability, causes agents to herd on one of the 2 arms. And so as a result, each of these groups is going to, each arm is going to be sampled enough times with constant probability. And then we're going to add this level 2 on top, in which they see all of the outcomes of the level 1s, and hence they see many samples of each arm. And so this 2-level thing is going to get regret, which is order t to the 2/3. And again, the intuition here is that level 1 agents are providing enough exploration to distinguish the better arm if the gap is large. And if the gap is not large, then we're not incurring that much regret by not learning which arm is the better arm. And so it takes a little bit of calculation. It's pretty standard calculation. I'm not going to go through it, but we have this, first we have to prove that in the level 1, we get an order k, omega of k samples of each arm with high probability, where k is the number of groups, of like paths that I've constructed. And by concentration bounds, we can show that the empirical mean in the first tau pulls of any arm is concentrated around its true mean, and therefore, because of the agents are picking stuff close to the empirical mean, each arm is going to get sampled. And then if the gap is large enough, the level 2 agents are going to pull the best arm, and you get t to the 2/3. So I'm not going to go through this. It's just a lot of notation, and it's very standard in the multi-arm bandit literature when you want to prove t to the 2/3. And why are we getting 2/3 here? It's because essentially the level 1 agents are exploring for us, and then the level 2 agents are exploiting the explorations of the level 1 agents. And explore then exploit algorithms, so we're just mimicking an explore then exploit algorithm, and they are known to get t to the 2/3 regret. And to improve on this regret, we have to implement adaptive explorations. So the question is, how can we use these subhistories to induce adaptive exploration among agents? And the idea is to leverage the cases in which the level 2 makes a mistake, in which the gap wasn't large enough and level 2 might actually try to pick the wrong arm. And so I'm going to make many copies of level 2. And in each of these copies, either the gap is large and so these guys are doing enough exploration for everybody above them, or the gap isn't large enough, in which case these guys, some of them are going to be picking the suboptimal arm, and hence they're going to do the exploration required for level 3. So here the adaptivity is on, was the gap large enough or not? So yeah, the analysis is going to have, it's going to be a case analysis based on the size of the gap, but the policy is just going to explore down here, it's going to exploit up there, and the middle level is going to explore if there's a clear winner among these levels, in each of these levels. And if there isn't a clear winner in each of these levels, then it's going to induce this level to do more exploration. And so this is how we get the adaptivity. And so if I set the parameters correctly, I can get t to the 4/7. As before, the proof is going to condition on good events. One is that level 1 explores enough. 2 is that there's concentration in the prefixes so that I get concentration around the empirical mean around the true mean. And then there's going to be this event that there's anti-concentration in level 1. So in each level 1 group, there's some group where each arm looks good and the other arm looks bad compared to the true mean, inducing more exploration. So as I said, the proof is based on this case analysis of the gap between the 2 arms. And if the gap is negligible, I don't care. I'm going to get good regret no matter what. If the gap is large, that's the case we were in before, level 1 did enough exploration to determine which was the better arm, and then level 2 and 3 agents exploit thereafter. But what we need to do to improve the t to the 2/3 is solve these intermediate gap cases. So if the gap is medium, then maybe level 2 is making some mistakes, but because they only see one of the groups of level 1. But in aggregate over all of the level 1 groups, the level 3 agents are able to identify the better arm. So we just lose on level 2, but level 3 has enough information to exploit. And then the interesting case here is if you do the calculations, you'll see there's still a gap between what we can allow here to get our regret bound and the negligible gap where we don't care anymore. So we call that the small gap case. And so for the small gap case, we're going to need this anti-concentration bound, where in each of the groups, like level 1 groups that a level 2 collection of people observes, there's some probability that they're making a mistake in each direction. And that's what's going to induce the extra exploration. So we use this anti-concentration bound to argue that there's this extra exploration in this level 2 group. And now the level 3 agents are going to pull the correct arm, not because they see all of level 1, but because they see all of level 2. And the level 2s have been induced to explore because the gap wasn't separated enough. So that gets us this improved bound, and if you do, there's a lot of things you have to balance, you're going to get t to the 4/7. But as I mentioned, you would like to get t to the 1/2. And again, the reason that we're not getting t to the 1/2 is because we need, we can handle large gap, medium gap, small gap, and negligible, but we need to subdivide this more. We need to do this again and again. So for any particular gap that's between the mean rewards, there's going to be some level that we want to be the one that does the exploration for the levels above it. And so we can try to create that construction by just repeating what we saw before. Now we can have these big group, this 3-level thing. We can replicate it many times and then put 4-level agents above it. And now, the 3-level agents in the smaller than small gap but larger than negligible gap case are going to make some mistakes, inducing exploration at this level, which lets the level 4 agents do the right thing. But of course, the problem with this construction is that I've blown up the number of agents in level 1. And recall that these guys are getting bad regret because they could be pulling the bad arm with constant probability. So I want to get a more like compressed version of this construction. And so the idea is to reuse information. So this is being very wasteful about the information that these guys are collecting. And so I can create a condensed version of this construction that reuses information. I don't have time to go into how that happens exactly, but the idea is that if I set up the subhistories correctly, then in this, remember this level L-1 is trying to explore the, each arm gets explored by the L-1 level in some groups. And then the guys above it are like, maybe in these groups, the triangle got lucky. So these guys are going to do more triangle exploration for me. And in these groups, the diamond got lucky. So these guys are going to do more diamond exploration for me. And notice that the histories that the red outlined people see is disjoint from the histories that the blue outlined people see, which is what allows me to argue that the middle layer here is going to be exploring. And then we get in the top layer, they get to see explorations of both types of arms. And hence they can exploit. And so that's the history they see, they exploit. And that allows me to get improved regret bounds. So I can go all the way down to approaching t to the 1/2. So in conclusion, I get optimal regret by revealing subhistories in a model with behavioral agents. The 2-level idea was to use focus groups. The 3-level idea let us improve our regret bound by adding group aggregators that helped us refine the exploration. And the L level got us is a way that you can reuse exploration in order to improve the regret bound even further. Thank you.
One question, if there is one.
So does this create a different problem of different people seeing different ratings? So Yash and I are both looking at Yelp, and I see 3-star and he sees 4-star.
Yes, this definitely happens in this policy because, like, if you belong to different focus groups, some arm might get lucky and some arm might get unlucky. So we need you to do these decisions independently. But yeah, that will happen.
Okay, thank you very much. We are going to take a 25-minute break rather than a 30-minute break, and we'll resume at 11 o'clock.